So now that we're a little familiar with some aspects of tree biology, I wanted to talk about compartmentalization. Uh, Basically, how trees are able to go about using the different aspects of how they grow and their anatomy to compartmentalize in the event that they're wounded or start becoming infected by microbes from the outside somehow. So overall, we've gone over various aspects of what composes a tree, and biomass of trees tends to be heavily concentrated in the trunk. And the reason for this is it's not a surprise, kind of. It provides the support for the entire tree. They need to grow taller to compete for sunlight with other trees in most forested areas. And therefore, the trunk is where biomass is concentrated for vertical growth. So what I wanted to point out here is that living trees are typically a lot less uniform than they look. In a lot of cases, if you're able to see a cross section or like the internal parts of a log, there's a lot more going on here a lot of times than meets the eye. And so as you can see, you've got in a lot of species, they form heartwood. And this actually is non-living tissue. It basically is a skeleton of sorts for the tree. Not that these other parts of it are not providing to the support of the tree, but it eventually it's like our bones. Our bones are alive, but there are parts of it that are composed of minerals and like are relatively non-living. And like that's kind of the same thing that's going on here with this heartwood. And the fact that it's non-living can be problems can lead to problems, as I'm going to point out here a little bit down the road. The next thing I kind of want to draw your attention to is this sapwood. So the xylem, the other part of the xylem here, this is where the active transport of water is typically occurring. Unlike the heartwood becomes inert. It kind of to some degree, like it's not used for transport anymore, and that area becomes focused on the sapwood. And the next big thing where the magic of tree biology really occurs is this vascular cambium layer, and it provides the separation between the xylem and the phloem, and it's where trees are able to keep growing, and basically like by widening that where it focuses the growth for both the xylem and the phloem. And within the phloem, this is the other vascular part of the tree. Basically, this is the area that the carbohydrates and sugars are able to work their way down. Then outside of this, you've got the periderm, which is just a nice way of almost basically saying the tree skin, which bark is part of that. And so I guess just to show you another perspective here, you can see that on this tree on the right-hand side, this cross section, it breaks down the heartwood from the sapwood. So then all this is technically xylem in here, but the sapwood is where a lot of the water movement and nutrient movement from the ground occurs. So here's another perspective cross section of a tree trunk, and the only thing I really wanted to point out here was that these vascular ray structures. So as the trees grow outward, they maintain these structures that also grow outward with them, and that will be important here for containing rot, as I'll try and demonstrate here in some future slides. So I wanted to take a little bit of an aside here and talk about how trees are different than some of the other tree-like things that we think of. Um, as we've mentioned, the state tree, sable palmetto, isn't even a tree at all. And the big difference here is kind of that internal structure that I was pointing out earlier. Uh, these plants, they act more uniformly inside than the trees do. They're more like a series of interconnected straw fibers, and huge portions of the stem are actively engaged in the movement of water. And in a lot of ways, it's better to think of palms almost as, and palm-like plants, as being more in common with like long blades of grass than trees that tend to break up the transport of water and nutrients into different sections of their biology. These plants tend to be much more uniform in dividing up the transportation of carbohydrates and water and nutrients. And so they also respond very differently physiologically to damage. And if these plants take damage, they don't seal up the same way that trees are able to. They kind of just have to take the damage and just live with it. They might have some chemical controls around where they're exposed, but those wounds will never completely cover up. These plants don't get wider as they grow. So unlike palms and other tree-like organisms, actual trees grow wider as they mature. They got to keep growing taller, they got to keep growing wider, and the solution that they've come up with is to have these, to have growth grow vertically as well as horizontally. And trees are potentially very massive organisms, some of the largest organisms in the world, and they are extremely long-lived at the same time, a lot of them. So, but they can't get out of the way if something were to cause harm to them, and they can't avoid damage in the way because, the way that animals do, because they're immobile. So therefore, they've evolved basically to absorb damage. And a lot of that comes from the structure and biomechanics of just being very sturdy. But in the event that they actually do take damage and are exposed to the outside world, they're not any different than us in many regards. If we have our skin peeled back and we get exposed to microbes, they have to deal with that the same way we would. And we have an immune system, and trees, in a sense, have an immune system but acts very differently and is driven by different mechanisms than what we're used to thinking about how their immune system works. So what we've got here is a giant chocolate wedding cake. Actually, it's a diagram of the different walls that trees use to block off decay from injury, where they've been exposed potentially to outside air and the microbial pathogens that could also make their way in with this air. And the idea here is that with basically cooperation of all of these various walls, that you can contain the rot that is occurring, the decay, the movement of the decay and the decay causing microbes with these various walls. So wall one is, these are xylem vessels immediately above and below where the injury occurs. They plug themselves up, and they also use chemicals when the tree is injured. And some of these plugs, they form kind of a weak boundary in some trees, but other trees, it can be much stronger, like in oaks. But still, overall, it's a pretty weak wall. And because of that decay, and some trees can advance pretty rapidly up and down the trunk. So wall two here, this is formed by growth rings. They make up wall two. And the transition from one ring to the next basically retards the advancing of the decay organisms. They have a tougher time moving across these growth rings than a uniform substrate like the standard woody area that is formed like each year that form the bulk of the growth rings. The darkened regions that are in there, they can alter the chemical composition of them, and basically that's how it is. This number 2 wall is trying to prevent the decay from moving inward to the center of the tree. So the rays that I pointed out earlier in one of the cross sections, they are what compose wall 3, and they have a greater ability to defend the plant for the tree from pathogens than walls 1 and 1-2, and that's because they're richer in starch, and that starch basically provides the energy needed to change the chemical compositions of the areas that within the rays there. And so this is a stronger defense, and it gives another way of breaking down the plant from decay moving onward. And so the next wall to think of here is wall number 4, and it's very similar to wall number 2. It's made by the growth rings. However, the big difference here is that it only occurs for new growth on the tree. It doesn't occur with older growth. So wall 2 is the previous growth rings. Wall 4 is everything that's newer. And actually, wall 4 is the strongest boundary. So when the tree gets this damage, it's able to determine where it needs to allocate a lot of its resources to recover, and the damage is around that is the epicenter of where the tree needs to focus on healing itself. And this wall 4, in order to prevent any of the new growth from being compromised, wall 4 has the highest concentration of chemicals to protect itself. And so I'll point this out here from another perspective. So kind of focus on this lower diagram. You can see that how the rays, the growth rings, all cooperate to contain an event that occurred at some point. This event where the tree was damaged was right here, where it's red. And wall 4 basically was able to contain all of this and prevent it from spreading to all of the new growth. So I kind of wanted to give a more longitudinal perspective here. As you can see, this would be wall 1, containing the horizontal movement. You've got wall 2, which is the older growth rings, preventing it from the decay from moving internally inward. And then you've got wall 4 here that has stopped the decay from moving in with the new growth. And here's just an actual tree cross section of what this would look like. You've got wall 2 and wall 3 are the rays, preventing it from growing around the sides so much with the and then wall 4 here is what happened with all protecting all of the new growth. And as you can see, it really didn't make a lot of headway here compared to some of these others. You can see the barriers breaking down a little bit, but on wall 4 that doesn't occur. But here I just wanted to point out how this would occur over time. So this is over the first year, where a wound would occur, all the walls start coming into play. And then this is a year or two in, wound wood around the outside has started being formed, trying to seal up the outside from any more air or pathogens getting in. And then you can see where wall 4 is forming, and this becomes the most crucial wall moving forward here. So, and here's a continuation. Here's the same year 1 in, but then as the tree develops over time, basically the decay becomes sectioned off and contained to one area, where this is where you would see discolored wood. If you were to cut this tree open, it would just look a little brown right here relative to everything else. And then if the tree is successfully able to recover, you wouldn't even be able to tell eventually. It would just start growing like normal. And that can happen in some cases, particularly when the trees are young, that they can recover from this type of huge amount of decay making it in, or decay organisms making it within inside the tree. And so this green area here basically indicates where the microorganisms have been able to establish themselves, and the red indicates where the barrier zones are most active and developing. So as you can see here, wall 2 is still in place, and with over time, the wall 4 develops, and you're able to get continued growth, and eventually the tree is able to overcome a lot of this damage. And not that a lot of this will go away over immediately, but at least the organisms that the tree is defending itself from won't be able to make a lot of progress if the tree is successful in containing the rot or the decaying organisms. And so if the tree is successful and lives to this point, and basically the organisms will be starved out from being able to access any source of carbohydrates to keep moving into other parts of the tree, and they'll be essentially just starved out. So, and this is particularly the case if the tree is able to fully seal itself. If that happens, they're cut off even from oxygen, from a fresh source of it anyway. And that's like the best case for trees in a lot of instances. And so why is it really important that the trees seal themselves in addition to containing the disease, is what you might be potentially thinking here. And the big thing that it comes down to is structure. So internally, a tree can decay, and this happens a lot of the time. If wall 2 is not effective, basically all of the heartwood can potentially rot out. But that doesn't necessarily mean that that tree is very structurally impaired if wall 4 is still very strong and the tree is able to keep growing outwardly. In that case, if a tree overcoming that wound but becoming hollowed on the inside, the tree basically acts like a giant cylinder. And cylinders can be quite strong. You think of like a silo or a big metal pipe. These are pretty strong structures, even though on the inside they're hollow. What's bad for a tree in the long run is, however, if it's never able to recover from the outside. If it's never able to seal up what's going on there, it can't start putting on more wood to basically keep all that weight in place that it needs to uniformly distribute over the entire trunk. And this is a big problem from a mechanical and structural viewpoint, if you think of what happens to like corroded pipes, for example, they break very easily there. And another perspective on this would be a can, aluminum Coke cans. They're basically cylinders as well. And if you were to tear the side of it, or even just punch in the side of it a little bit, that tree or that can is much more likely to be crushed at that weak point than if it were completely uniform and weight were applied on both sides of it. And as trees start to grow older and start becoming more mature, it can be more problematic for them to respond to potential damage that occurs to them. And as you can see here, I've got two examples of damage that happens on the stem. And this tree that's on the left-hand side here is in a much better situation than what's going on the right-hand side. This tree might be able to recover and keep growing basically with this response wood into a cylinder of living tissue that can support the weight, fully distribute the weight of this tree. On this other side here, this tree was already very mature to begin with, and it looks like it had a pretty sizable damage, piece of damage occur to it, and it's probably not going to be able to recover from this wound. It'll ultimately be immortal to this plant. So here's just another perspective of why, of what can happen if a tree is successful being able to seal off this decay with wall 4, and why wall 4 is the most important wall. And if you take anything home today with it from this, it's that trees want to keep living. And if a tree is an effective compartmentalizer, it's going to have a good wall 4, and it will be able to remain as a cylinder. However, it's still not ideal to get decay growing inside of you and basically eating your skeleton. So, and you know, different trees have different strategies. So some trees are pretty good at compartmentalizing. Some examples for trees that we have here that are pretty good at it: trumpet tree, Tabebuia hadranthus, maples, most elms. Live oak is a very, very good compartmentalizer, very full of you know, various tannic compounds. Crepe myrtle is another one, and mahogany down in South Florida. Some weak compartmentalizers: laurel oak and water oak, avocado, various orchid trees, most willows. You notice like what's going on here, a lot of the time willows are some of the fastest growing trees. And basically, like the tree, there are evolutionary trade-offs. Either you're gonna try and be a fast-growing tree and compete with your neighbors that way, or you want to be a tree that's going to be able to survive and make it out in landscape. Willows decided that it was more worth it to grow fast, and you know, it's tortoise versus the hare basically, and the willows are the hare, and they don't have as much of an ability to fight off these wounds. And so it's true for most of these trees, actually. So sugarberry we have here, and redbud as well. These are all trees that don't compartmentalize particularly well here in Florida. And almost everything else is somewhere in the middle if it's not on these two lists. So why is this all important? Well, on the next section here, Jamie Lynn's gonna point this out. And you know, there can be a lot of damage in other places on the tree, and the branches are where we have a lot of managerial control over the growth of trees. And so that's very important. This all crosses over to why it's very important to do your cutting the correct way. So because the stem, you want to prevent as much of what goes on, like in cuts and things that happen potentially in the branches, from making its way to the stem, where the tree is much more susceptible from dying if it gets infected. So, ultimate lesson here: trees do not heal, they seal. That's how they stay alive. They don't heal the same way we do, where that tissue remains intact. If they lose their tissue to decay, it's gone. But they can overcome it with as they continue to grow. So, and if at all possible, avoid damaging tree trunks, because that is where the trees are the most vulnerable. It's their greatest strength, but also their greatest weakness. So with that, I'll leave it off here to Jamie Lynn.